everyone. I'm Yuhan Yao. I'm a second-year graduate student in astronomy at Caltech. For my research, I study supernova explosions that's discovered by the telescope shown here in this image. With a mirror that's 48 inches in diameter, it's located at Mount Palomar, that's roughly 120 miles south of Los Angeles. Today, it's my great pleasure to share with you some of my field stories through the discovery of supernovae, and specifically how studies on the Palomar Mountain has been pushing the field forward in the past century. It's a bit unfortunate that we have to make this talk virtual in the current state of the world, but I really hope that after social distancing is over, I can meet you in person and start a live Q&A session. Okay, so why do we care about supernovae? Well, in the nucleosynthesis point of view, we are all stardust. Because in the very early universe, after the Big Bang, there is only hydrogen and helium. The first stars composed of only hydrogen and helium appeared about 100 million years after the Big Bang. It is in the core of those very massive stars that heavy elements of carbon, nitrogen, oxygen, neon, and magnesium are for the first time fused into existence. During the evolution of a massive star, as it continues to create heavier and heavier elements, eventually it will run out of fuel. And at that time, you don't have more energy to support the star. The star will collapse and then detonate. The core will collapse into a neutron star or a black hole, both of which are very dense and compact. And the outer part of the star will be ejected into space, spreading new atomic elements into the void. There is the subtle difference between the evolution of high mass and low mass stars. For low mass stars, such as our sun, during its evolution, the outer part of the star will be expelled as a planetary nebula, and the core will evolve into a white dwarf composed mainly of carbon and oxygen. When the temperature of the white dwarf gets high enough to ignite carbon, it will undergo a series of nuclear fusion that will completely disrupt the white dwarf and create something called a type 1a supernova, or thermonuclear supernova, after which there will be no remnant left. And this type of supernovae is a major source of iron in the universe, and iron is the element that makes our blood red. During the 13 billion years between the first generation of stars to the formation of solar system and then biological life, lots of stars end their lives as a core club supernova or a type 1a supernova, providing the universe with heavy elements such as carbon, nitrogen, oxygen, and iron, which is exactly the elements that our own human bodies are made out of. So when you think about this, we are actually made up of raw ingredients created in the stellar explosions of different masses of stars. Another very important aspect of supernovae is that they can be used to study the expansion of the universe. We know that the universe was created in a Big Bang some 13 billion years ago. And ever since then, the universe has been expanding. But astronomers wanted to know more about the nature of this expansion. For a long time, there are two ideas. One of the ideas is that the expansion of the universe will be slowed down and eventually come to a halt, after which it will start to contract to a big crunch. And the other idea is that the universe will continue to expand forever. But how can astronomers know which of the models is correct? Well, one of the simplest way of doing this is to accurately measure the distance of very far away galaxies and to compare those measurements with the predictions from the models for those particular galaxies. And to precisely determine distances that's huge across the cosmos, we can look at supernova. They are very bright, so they can be seen even in very far away galaxies. And more importantly, astronomers have found that type 1a supernovae all have the same intrinsic peak luminosity, which means that their distances can be inferred from how bright they appear to us on Earth. This property has made type 1a supernovae an ideal calibrator for measuring distances. So by 1990s, two separate research teams has started to carefully observe those stellar explosions. And an important result from their observations is that the universe is not only expanding, but is doing so at an ever faster rate. This result is so unexpected because up to that point, the more popular belief is that the expansion of the universe will slow down due to the attractive force of gravity exerted by the matter in the universe. But it turns out that the universe is much more interesting than that. So their discoveries were awarded the Nobel Prize in Physics in 2011 because it confronted us with new physics here. So why is the universe expanding at an ever faster rate? Well, the well-accepted explanation is that about 2/3 of the universe contains some form of the mysterious dark energy. We don't know what the dark energy really is. So although we know that the universe is expanding right now, here is the stage we are at right now, we don't know how it will end. Maybe, just maybe, the dark energy will get weaker in the future. In that case, we will still have this big crunch. And if the dark energy stays constant per unit volume with time, then you will have this sort of exponential expansion. And perhaps the dark energy will get stronger in the future. And in that case, the whole universe will be ripped apart. We really want to know how the universe will end. So that's where continued study of supernovae can help tell us. The field of modern supernova research began in 1934, when two of the greatest astronomers in the 20th century postulated that stars can explode and create neutron stars. They invented the word supernovae to describe such explosions. In their paper, they recognized that classical novae are cataclysmic burning on the surface of white dwarfs, but supernovae are catastrophic explosion of stars. They are two distinct families of optical transients that last for days, for weeks, for months, but they disappear on us. One of the two astronomers, Walter Budd, was originally from Germany, and he joined the staff at Mount Wilson Observatory here in Pasadena in 1931. Budd was a publicly shy, rather delicate man with pointed ears and always wear a bow tie. Sometimes his hands would tremble from nervousness, but somehow when Budd took the pedal of the telescope, all the shaking would stop, and he took masterful photographs of the star fields, discovered stellar populations, among many other things. The other astronomer, Fritz Zwicky, received his education in Switzerland and moved to California in 1925. Apart from being an outstanding astrophysicist, Zwicky also had successful careers as a pioneer in jet propulsion, as a military engineer, as an explorer of space using rockets, and as a builder of libraries in many countries to repair the destruction made from World War II. His brilliant ideas, such as the existence of dark matter, were too far ahead of his time to be understood and accepted. So sometimes when Zwicky thought other people were stupid, he would make pretty harsh criticism to them. And as a result, he had the reputation of being eccentric, and he did not get along very well with other scientists. Anyway, Zwicky really wants to watch a supernova going off to prove that Budd and him were right concerning the existence of supernovae. So how can you do this? Let's imagine that we have a beautiful image of the Pinwheel Galaxy M101 from an older record. And when a supernova explodes, if we take a new image of the same piece of the sky, and if we compare the two images, we may see that there is a new flash of light here at the bottom of the new image. And this kind of image comparison and subtraction is the technique to search for cosmic fireworks that change in brightness. Zwicky was aware that the 100-inch telescope at Mount Wilson can only observe a small patch of the sky at a time. He would need a wide-field telescope to monitor a large number of galaxies, and thereby maybe increase his chance of catching the gleam of a supernova. In 1935, Zwicky heard that the German optical technician Bernhard Schmidt invented a powerful type of telescope that can focus light accurately over a wide field of view. So he bought a little 80-inch from Schmidt and installed it near the summit of Mount Palomar. In 1936, Zwicky started taking pictures of the sky and looking for changes from one photographic plate to the next. Believe me, it was hard work, but Zwicky was a really determined physicist. With the help of a single assistant, he found 19 supernovae until World War II interrupted his survey. His search yielded two results of far-reaching consequences in our understanding of stellar evolution, namely that there are two types of supernovae, and they are created in a nuclear fusion chain reaction. Those two types of supernovae are nowadays termed as type 1a supernovae and core club supernovae, as we saw before. Due to the success of the 18-inch in 1930s, resources to build a larger Schmidt with a 48-inch aperture were committed in 1937. Bud and Zwicky supervised the construction of this telescope, which saw its first light in 1948. Thereafter, it was firstly used for a total sky survey and became available for supernova search in 1959. Roughly at the same time, two more telescopes were being built at the Palomar Mountain. One of them is the 60-inch telescope that had been primarily used for rapid follow-up observation of things discovered by other surveys. It's not the kind of Schmidt that the 48-inch was, but it has larger aperture, so can observe fainter objects. The other one is the 200-inch, also called the Big Eye. For almost half a century, it reigned as the unrivaled leader in astronomy at optical wavelengths. We can easily spend a whole day just talking about the evolutionary discoveries made from this telescope, but I think it's most important to remember that it is not good at finding things, not for any surveys, but for the detailed spectroscopy of a single object. So what is spectroscopy? Well, you may have the experience of putting a prism in front of the sun. The white light will disperse into different colors. The redder colors have longer wavelengths and less energy, while the bluer colors have shorter wavelengths and more energy. The intensity of colors as a function of wavelength is called a spectrum. Now, different atoms or elements absorb or emit different colors of light, which imprints the telltale signatures in their spectrum. So if you put a spectrograph along the optical path of the 200-inch and use it to observe a supernova or like a star, then you can figure out what those objects are made of. And that is how we learn that core club supernovae contain hydrogen, but type 1a supernovae contain heavier elements but not hydrogen. Okay, going back to our story of the supernova search. Between 1959 to 1975, the 48-inch was used pretty successfully for the purpose of finding supernovae. In 1961, Zwicky induced the International Astronomical Union to establish a committee for supernova research. And after that, this field of astronomy has moved on an international scale, with many observatories around the world joining the game. So ever since 1997, the Lick Observatory supernova search, led by UC Berkeley, has been the most successful in finding supernovae. And the Berkeley group was also one of the two teams that discovered the accelerating expansion of the universe from the observation of type 1a supernovae. In the late 20th century, the Palomar smaller telescopes spent the majority of their time in other fields of astronomy, but entering into the 21st century, there were concerns that the financial investment for the 48-inch and the 60-inch was pretty expensive, but the science output was not very productive. In 2006, Caltech professor Sri Kulkarni became the chair of the Caltech Optical Observatory. He wanted to shift Palomar's focus back to the search of supernovae, and more precisely for the search of optical transient phenomena in general. There were two motivations to do that. The first is that if you look at this diagram of cosmic explosions, namely the peak luminosity as a function of the light curve evolution timescale, then you can see maybe type 1a supernovae are more luminous at peak compared with core club supernovae, and they evolve faster. But what is immediately noticeable is that there is a wide gap between supernovae and classical novae. So Professor Kulkarni thought maybe there are a lot more new types of transients exist in this gap, such as like neutron star mergers, stellar mergers, or anything else beyond your imagination. We didn't discover them because maybe they are intrinsically rarer and fainter. The other motivation is the rapid advance in technologies of machine learning, engineering, and computer science. Before 2006, the way people have been finding supernovae is one at a time. It was a manual affair. Normally, you need to have someone observe a part of the sky for nights, analyze the data, and compare with older records to then find a supernova. The Berkeley group can find one supernova every 3 nights by observing nearby galaxies, while others were spotting one per month. So the Palomar observers wonder, why not make this an industrial operation? Why don't we employ automation throughout the entire process? And there came the Palomar Transient Factory, PTF. The idea is to take over the 2 smaller telescopes at Mount Palomar to focus on what they can do best. The 48-inch will take wide pictures of the sky and compare with the older ones. Once something new shows up, the 60-inch will verify if it is really an object of interest by taking pictures in 3 colors. And for the most interesting transients, for example, if it exists in the gap between classical novae and supernovae, or if it evolves faster than anything we've ever seen before, then we will use the 200-inch spectrograph to derive its composition, its velocity, temperature, so we can have some clues of the nature of the beast. Unlike old times when the search of transients can be done by just a few people, to achieve the ambitious goal of PTF, we need experts in image subtraction and processing to handle the large data flow. We need experts in machine learning algorithms to tell if the subtraction looks real or not. We need software engineers to make everything automatic, and we need clever observers to plan for follow-up observations. So PTF went online in 2009. Within 1 year of operation, it not only detected, but also classified 700 supernovae. And this will not be possible without the collective efforts between different institutions all around the world. One of the breakthroughs of PTF is the early classification of infant supernovae. I told you before that astronomers have been using type 1a supernovae as a standard calibrator to measure the distance of galaxies. And this leads to the discovery of the accelerating expansion of the universe. However, a major embarrassment for us astronomers is that we actually do not understand the explosion mechanisms of those type 1a supernovae very well. And through the early observation of those baby supernovae hours after the explosion, we can put a more stringent constraint on their pre-exploding white dwarf radius. We can gain more information about their environment and thereby maybe figure out how do the white dwarf explode to produce type 1a supernovae. At the end of the PTF survey, we find evidence in support of two different exploding channels. In one of the scenarios, there are two white dwarfs orbiting each other, and as time goes by, they get closer and orbit each other in a faster way. At a certain point, they will collide and merge with each other, create the type 1a supernova. In the other scenario, this is the white dwarf. It accretes matter from a companion star that's nearby. And as it gets heavier and heavier, at a certain point, its pressure cannot support the gravity, so it's gonna explode. It is pretty surprising that nature creates type 1a supernovae in more than one way. A major bottleneck in modern supernova research is that we can detect many transients, but there is not enough observing resources to classify them. The PTF team has access to the Palomar 5-meter telescope about 2 nights a month, and the CAC 10-meter telescope about 1 night per month. In rare cases, we are lucky enough to get observing time on the Gemini 8-meter telescope, but taking all of those together, it's still not enough. So to improve this situation in 2013, we upgrade the Palomar 60-inch telescope. Previously, it was only used for multicolor image in 3 filters. And now we put a new instrument, which is called the Spectral Energy Distribution Machine, SEDM, to enable low resolution spectroscopy. There were lots of efforts put to make SEDM fully automatic, which means that as soon as something interesting is detected by the 48-inch, the SEDM will take a spectrum of this source. And as soon as the data is taken, there will be automatic data reduction pipeline to deal with the raw data. And within only 5 minutes, the algorithm will classify the spectrum and tells you the classification. So this is pretty major achievement. To reflect this upgrade, we rename PTF as Intermediate Palomar Transient Factory to reflect this change. And this also marks the start of the second phase of this operation. One of the great results from SEDM is the discovery of a strongly lensed type 1a supernova in real time. So what is a lensed supernova? Well, in the case of a perfect alignment between a distant supernova, an intervening galaxy, and the observer, the light from the supernova will be deflected, and from Earth, we will see multiple images of the same supernova, but with magnified signals. And this is a phenomenon known as strong gravitational lensing. In 2016, IPTF detected a source on top of a distant galaxy that's 50 times more luminous than a typical type 1a supernova. But the SEDM spectrum shown us in real time that this is a 1a supernova spectrum. So we know immediately that this source is probably strongly gravitationally lensed by this intervening galaxy. And this then give us strong scientific justification to trigger the Hubble Space Telescope and the CAC telescope in Hawaii to get high resolution images. This is the CAC image that we get from adaptive optics. The different sources you see inside the circles it's not from different sources, but actually different images of the same source being gravitationally lensed. And because type 1a supernovae have roughly the same light curve shape, we can measure the time delay between those images. And the interesting is that if you have a dozen such lensed type 1a supernovae, you can constrain the expansion of the universe as good as many other methods. At the end of the IPTF experiment, when we go back and look at this diagram for cosmic explosions, we find ourselves immersed by the various type of optical transients that nature rewarded us with. And then on August 17, 2017, something really unprecedented happened. For the first time, astronomers detected the gravitational wave signal from the merger of a double neutron star. This event was relatively faint and it evolved pretty quickly, so it is at this region of this diagram. Now, the reason we know it's a double neutron star merger is that 2 seconds before the detection of electromagnetic light, we also detected gravitational waves from the same source by 2 gravitational wave detectors. One of them is the US experiment LIGO, and the other is the Europe experiment Virgo. What was really happening was that the 2 neutron stars inspired and emit gravitational waves that can be detected by 100 seconds. And when they collided, a flash of light in the form of gamma ray is emitted and seen on Earth about 2 seconds after the gravitational wave detection. Now, gamma ray has the highest energy in the electromagnetic spectrum. In the days and weeks after the gamma ray detection, we also detect X-ray, ultraviolet, visible, infrared, microwave, and radio waves from the same source. Further spectroscopic observation revealed signatures of recently synthesized material, such as gold and platinum. Okay, at the beginning of this talk, I told you that our own human bodies are made up of elements that synthesized in stars, in the explosion of stars, in supernovae. But before 2017, August 17, we had a decades-long mystery of where is the production place of more than half of elements more massive than iron. And the detection of gold and platinum in this transient event told us that the rings on our hands, that the gold medals awarded to Olympic game champions are actually synthesized in neutron star mergers. This event was such big news because it marks the beginning of the joint study of transient phenomena between gravitational waves and electromagnetic surges. Now, gravitational wave is the stretching and squeezing of space-time produced when you have a large amount of mass. The amplitude of gravitational wave is so tiny that only the most sensible detector in the world can detect it. And one of them is LIGO. The way LIGO works is that you have a laser of light source. It gets splitted at this beam splitter into 2, and it getting reflected at the mirror. And the 2 rays of light get interfered at the detector. Now, because you have gravitational waves, you have this stretch and strain in space-time. The distances of the 2 arms actually have a tiny bit of change. So you can see sometimes a bright spot at the detector and sometimes a dark spot. And by measuring those interferes, you can measure the gravitational waves. And now we detect them. But we also want to know where the gravitational wave come from on the sky. And that is where you need a network of gravitational wave detectors. You need to measure the time delay of the gravitational wave signal at different sites. And in this way, you can do localization. Up to now, we have this LIGO Hanmer Observatory in Washington State. We have LIGO Livingston Observatory in Louisiana. We have Virgo in Italy. And there's also 3 observatories under construction, Kagura in Japan, LIGO India, and GEO 600 in Germany. But astronomers was so lucky on 2017, August 17, because you can see that this event was localized by LIGO Virgo in a very small region. So all of the astronomers in the world can point their telescopes in this region and search for lights that newly appeared on the sky. But for the vast majority of LIGO-Virgo localized gravitational wave events, as you can see there, their localization is actually pretty poor. So you need to search for a large area of the sky in a very short time. Because if you do this too slow, then the electromagnetic radiation signal will fade away between you can go to the real direction of the transient. So we ask ourselves again, can we improve the intermediate Palomar transient factory further to give it a faster survey speed? So we look at the dome of the 48-inch. This is the sky. You have light traveling from the sky down to the primary mirror. The light gets reflected and be collected at the focal plane. And as we look at the focal plane, we came up with the idea of building a much more powerful camera to put it here. And here came the third phase of this project. We name it as a Zwicky transient facility in memory of Fritz Zwicky, because his work of supernova research at Mount Palomar deserves to be remembered. So the idea of ZTF is to build a much larger camera without blocking light traveling down from the sky to the primary mirror. So it's like turning your computer into a laptop or a cell phone. You have to worry about all of the extra space that you used up. We have engineers doing the assembling in a clean room. They managed to get all of the very delicate sensors together in a very tight space. And now what you have, it's a detector that's 100 times more sensible, which means that your exposure time can be 100 times shorter. We have the robot to change filter. We have telescope slews under computer control and settles within 8 or 9 seconds with the shutter closing. So this is the first light ZTF image of the Orion Nebula. Unlike in the PTF and IPTF time where we only survey the sky in one filter, for ZTF we are taking pictures in more than one colors so that you have these images and light curves in different colors. Within the first several months of the ZTF operation, we collected more than 100 type 1a supernova light curves with this beautiful sampled data points. And here the color information is very important because for type 1a supernovae, there are explosion mechanisms that predict where the early time flux in the bluer filter should be higher. And there are also models that predict the flux in the redder filters should be higher. So by comparing the difference in the flux measurement at early time for a sample of type 1a supernovae, you can actually figure out which of those models is the dominant channel for the explosion mechanisms of white dwarf to produce type 1a supernovae. And that is something that has never been done before. And we are not satisfied by only looking in the optical. We also want to go to a longer wavelength in the electromagnetic spectrum. The infrared light is not visible to our eyes, but it opens a new window to the dynamic sky. For example, for transients in dusty regions, they will emit more light in the infrared than that in the optical. And also in the late time evolution of many neutron star mergers or supernovae, their emission in the infrared is also stronger than that in the optical. So at the same time that we build the Zwicky transient facility, Caltech professor Monzi Kasliwa led this survey in the infrared, which is called Cattini IR. It is also located at the Palomar Mountain. So just to give you a sense of how large the field of view of Cattini and ZTF is, compare with that of the PTF and IPTF camera. For scale, this is the moon and this is the Andromeda galaxy. The exposure time of CTF is pretty short, which is only 30 seconds. And this gives CTF a survey speed of almost 4,000 square degrees per hour. We can do a simple calculation here. The whole sky is 4 pi, which is 42,000 square degrees. At a specific night, at a specific location on Earth, we can actually observe a little more than half of that. So that's more than 20,000 square degrees. With a survey speed of 4,000 square degrees per hour, in a little more than 5 hours, you will run out of sky to observe, and that is pretty wild. In addition to a very fast survey speed, we also have a team that never sleep. So Professor Kasliwa also arranged this growth collaboration with a global network of telescopes for follow-up resources. So the idea is that as soon as the sun is about to rise at the Palomar Mountain, you can still take a spectrum by going to the west. First, in the island of Hawaii, and then in Japan, in Taiwan, in India, and etc. As the night sets in each of those mountaintops, you can always collect data and beat the sunrise. To demonstrate why a fast survey speed with a global follow-up facility is important, I'm showing you here in orange the localization of a gravitational wave event detected by the LIGO-Virgo collaboration on April 25th, 2019. So as you can see here, the localization is again pretty poor. The transient event can actually be here, 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 here. We don't really know because the uncertainty is very large. So within the first 2 nights, CTF and Cattini both conducted the search in the localization maps. Here, each of the square is 1 CTF pointing, and at the bottom, each of the square is 1 Cattini pointing. So in the south region, we cannot see it because Palomar is in the north, but within only a few nights, we are able to cover most of the high probability regions in those sky maps. And after this search, we have a few candidates. So just to show you some of them, this is the new images, and this is the older records. You can see the point source here at the center of those pluses has newly appeared that can be the neutron star mergers. So we use the growth follow-up resources to classify all of them, but none of them turn out to be the electromagnetic signal of double neutron star mergers. In the past year, CTF and Cattini together have searched for 13 gravitational wave events detected by LIGO-Virgo, and we have tried our best to search for the electromagnetic signals, but in the end, we found no bona fide candidates that look similar to the first binary neutron star mergers that we detected from the LIGO-Virgo triggers. But it doesn't mean that our searches is not successful. Non-detections is very, very important because it tells us that actually most of those double neutron star mergers, their emission in the electromagnetic spectrum is actually much fainter than the first one we detected on 2017, August 17. Okay, up to this point, if you are also interested in CTF science, you can actually help improve this project by visiting a program launched at the Zooniverse website. So it is this link. For a set of new image or the records and the subtraction, there will be guidelines to instruct you how to tell if the subtraction looks real or not. So there has already been a few 100,000 real and bogus events being classified by citizen scientists, and those will serve as a valuable data set to improve our machine learning algorithms. Moving to the future, one of the major missions to find transients will be this Large Synoptic Survey Telescope, which is also called Lyra-Rubin Observatory. With a mirror that's 8 meters in diameter, it can probe much fainter events than CTF can do. So to prepare for the large data flow that's going to be produced by LSST, the software pipeline of LSST is currently being tested and developed with the data flow from the Zwicky Transient Facility. It is not possible to cover all of those fruitful discoveries made from the exploration of the transient sky, but I hope that I have shared with you some of the science results that you also find exciting. To end this lecture, I would like to quote George Ellery Hale, who was one of the founders of the Palomar Observatory and Caltech. In the 1928 April issue of the Harper's Magazine, there appeared an article which starts with the following sentence. Like buried treasures, the outposts of the universe have beckoned to the adventurers from immemorial times, and through their provision of instrumental means, the sphere of exploration has rapidly widened. 100 years ago, Hale had this vision that larger telescopes will rock astronomy, and he made it. He was actually the builder of the Mount Wilson 100-inch and Mount Palomar 200-inch telescopes. 100 years later, we astronomers are standing on the verge of another evolution of big telescopes. There are currently 3 30-meter class telescopes being built. But at the same time, I'm equally astonished to see how those very brilliant scientists at the Palomar Observatory came up with those novel, fantastic ideas to improve both the hardware and the software of those smaller telescopes on Mount Palomar. I feel very grateful that this 48-inch telescope that's housed CTF is still doing cutting-edge supernova science, even right now in 2020. Thank you for listening. Bye-bye.